Hey everyone, and welcome. On behalf of Forge College, I am absolutely thrilled to be your host for today's explainer. Today, we're diving deep into the microscopic, granular world of Ethereum. We're going to look right under the hood at EVM bytecode execution and contract calls. So if you've ever wondered what literally happens when a smart contract runs, step by microscopic step, you are definitely in the right place. Go ahead and grab your digital magnifying glass.
Now, I know exactly what some of you are thinking. Wait a second. Weren't we just on Solana? And yep, you hit the nail on the head. In our last session, we were busy creating and signing transactions using the Solana CLI, just soaking in that high-speed, parallel processing breeze. But, well, in the world of Web3, we got to be adaptable, right? So we're throwing a bit of a curveball today. We are trading in our Solana beachwear for some heavy-duty hard hats, because we're stepping right onto the factory floor of the Ethereum virtual machine. It's time to get our hands dirty with some serious, state-changing mechanics.
Okay. Here is the master blueprint for today's factory tour. We've got 1. Welcome to the EVM. 2. Opcodes and gas tracking. 3. Memory versus persistent storage. 4. Hitting the revert button. 5. AI and local tracing. And 6. Preparing for block finality. Let's just jump right in.
Section 1. Welcome to the EVM. I want you to imagine we're shrinking down, kind of like Ant-Man, right? Into the foundational gears of Ethereum. We're bypassing that high-level Solidity code you're probably used to, and we're dropping straight down to the raw bytecode level. To understand this factory, we really need to understand its gears, which are called opcodes. An opcode is basically the fundamental mechanical operation of the EVM. It executes step by step, and crucially, this is huge, it consumes gas. Every single time a gear turns, whether it's adding numbers or storing data, it costs gas. There are absolutely no free rides in this factory. Every single action has a computational cost.
Section 2. Opcodes and gas tracking.
So, knowing that every single gear turn costs something, how do we actually track it? Well, in our execution ledger, we have basic opcodes like add, which handles simple stack arithmetic and costs a fixed, very low amount of gas. Nice and cheap. Then we have sload, which reads from storage. Now this one costs more, but it dynamically becomes cheaper if the storage slot is already considered warm, meaning it was recently accessed. SSTORE writes to storage and has a wildly dynamic cost depending on exactly what you're writing. And then there's call, which reaches out to external contracts, and that charges a base gas fee plus a stipend. The big takeaway here is that gas is not just some flat fee you pay at the door. No way. It's an active, ticking taximeter for each specific mechanical step the EVM takes.
Which brings us to a really crucial point. Gas accounting is an incremental, opcode-level ledger. When you estimate gas for a transaction, you're not just pulling a number out of thin air. You're actually providing a strict budget that has to cover the cumulative per-opcode costs of every single gear turn we just talked about. Plus, the intrinsic gas charged up front just for submitting the transaction in the first place. And if your budget runs out before the machine finishes its work, well, it's not pretty. We'll get to that exact scenario in just a second.
Section 3. Memory versus persistent storage.
Now, on this EVM factory floor, not all workspaces are created equal. There's actually a very clear divide. On one side, we have the ephemeral execution state, which includes the stack and memory. Think of this as your temporary workbench. As soon as the contract finishes executing, this space is wiped completely clean. Just poof, gone. On the flip side, we have the persistent state, or storage. This is the permanent vault. Writing data here means it stays on the Ethereum blockchain literally forever, which, as you might guess, makes it incredibly expensive to use compared to that temporary stack or memory.
Let's zoom in on those permanent writes for a moment. Opcodes like STSTORE physically write data to that permanent vault. Similarly, Create initializes entirely new contracts right into the persistent state. Because these actions permanently burden the network's hard drives, complex, dynamic gas costs apply. For instance, thanks to EIP 2929, writing to a storage slot you've never touched before, what we call a cold read or write, is going to cost you significantly more than interacting with a warm slot you've already accessed during that same transaction. It's essentially the EVM's way of forcing you to be highly efficient with the permanent vault.
Section 4. Hitting the revert button.
All right, we've talked about how precise and expensive this machinery is, but what happens when the factory machinery jams, or an exception occurs, or a require statement fails? Well, this brings us to the absolute golden rule of EVM execution. Ready? State is rolled back, but gas is gone forever.
I like to think of the EVM as the most strict, unforgiving vending machine in the entire world. You put your money in, that's your gas, and you make your selection. But if the snack gets stuck against the glass, or if the transaction fails for literally any reason, you do not get the snack. The state of the machine just resets. But the vending machine, yeah, it keeps your money. The gas used up to that exact point of failure is spent and completely gone. No refunds.
Just to really drive that home, reverts explicitly undo persistent state rights, but they leave the execution gas consumed. It is absolutely crucial to make a clear distinction between what temporarily happened during execution, the gears that turned, the gas that burned, and what actually persists after the settlement of the transaction. If a transaction reverts, the blockchain looks as if those state changes never happened at all. But believe me, the gas ledger definitely remembers that you tried.
Section 5, AI and local tracing.
So, the big question. How do we avoid burning our precious gas on failing transactions? Well, by building a rock-solid tracing workflow. We can do this using a really slick 4-step loop. Step 1, generate an initial draft trace using an AI assistant by just feeding it your bytecode. Step 2, verify that draft by running the exact same bytecode through a local VM tracer to get the undeniable truth. Step 3, annotate the trace, carefully marking exactly where state changes or reverts happen. And finally, Step 4, improve the trace by reconciling any differences you spot between your AI's draft and the local VM's hard data. This loop literally empowers you to produce perfectly annotated execution traces.
Now, to do this properly, you need the absolute truth, right? And that truth comes from authoritative testing via local tracers like Ethereum JSVM. We highly recommend spinning up a simple node script with a deterministic local VM. Why? Because, let's be honest, AI can sometimes hallucinate or estimate gas costs incorrectly. A local VM like Ethereum JSVM, though, runs the actual EVM logic. It doesn't guess, it just executes. It gives you the absolute, undeniable mathematical truth on opcode sequences and exact gas consumption.
When you go to compare your AI trace to the local VM, you're going to want to use this validation checklist to ensure both the syntactic correctness and the semantic accuracy of your work. First off, check that the opcode sequencing is exact. No skip steps. Second, ensure your stack snapshots are perfectly consistent from one step to the next. Third, verify that any state changes, like those STOREs we were just talking about, are accurately marked. And finally, the ultimate sniff test. Your individual gas deltas for each step must perfectly sum up to the total gas used reported by the VM. If all those match up, you've nailed it.
Section 6. Preparing for block finality.
All right, now that we've totally mastered the micro level, let's zoom back out for a second. We need to connect our microscopic, granular view of the EVM's gears back to the macroscopic reality of the entire Ethereum network. And here is exactly where it all comes together. Validated per-call state outcomes map directly to block-level state commitments. Everything we just traced, every STOR that didn't revert, every byte of data that successfully made it into the permanent vault, that is what actually matters to the network. Understanding exactly which storage rights survive the contract call is the exact preparation we need for understanding how transactions are grouped into blocks. And actually, we'll be covering that in our very next explainer.
So, I'm going to leave you with this final thought to chew on. Are your storage routes ready for the block? Because honestly, if you can trace a transaction all the way down to its opcodes, you know exactly what is and what isn't making it onto the blockchain. And that wraps up our factory tour of EVM bytecode execution and contract calls. This explainer was proudly made by Forge College. If you want to master these concepts, get your hands on some actual tracing scripts and explore a whole universe of other Web3 topics, I highly encourage you to visit forge.college to learn more. Thanks so much for joining me on the factory floor today, and I'll catch you in the next one.